Okay, so what we're going to look at today is we've had charges suspended in a field, right? Now, to get them suspended, you'll remember, don't write this down, the wave force and the electric force must be equal, balanced. Now, you could probably realize that to get them balanced might be a bit of a trick, and so sometimes you might have gravity, which is greater, or you might have the electric force, which is greater. In that case, you're going to have a net force, which means the object's going to forces cause, starts with an A, acceleration. So it's going to accelerate. This is no different. The topic that we're going to look at today is no different than if you've got, say, an applied force of 100 newtons and a friction force of, say, 20 newtons. Same idea, horizontal movement, the only difference being vertical, and the masses are really small, but the steps, the ideas are all the same. Okay, so if you can sort of keep that in mind, it really shouldn't be that much of a challenge, that much of a stretch. Okay, let's begin. Now, let's write down, I know some of you hate doing this. Imagine how much I hate doing it because I've done it so much. Okay, but it really does help if you write down what you know. Identify those numbers out of the problem. 1.0 times 10 to the minus 4, that's the mass. The charge is 3.2 times 10 to the minus 19. That's a Q. We use Q for charge. Do you recognize why it's 3.2 times 10 to the minus 19? Like our alarm bell's going off? Oh, that's how many Elches? It's 2, right? 2 Elches. The plates are 1.5 centimeters apart. The electric field strength is 1 times 10 to the 15. Not minus. Newtons per coulomb. Determine the net force on the object. Now, I've given you a lot of preliminary information here. Before I can get the net force is the sum of the forces, so that's going to be the weight force plus the electric force. So I need to find what those two are, and then we're going to add them together, right? Is the weight force easy to do? Generally, yes. Mass times gravity. 1.0 times 10 to the minus 4 times minus 9.8. Is the minus in minus 9.8 important? No. Age-old question. No. Does it ever hurt to make it negative? No. And then see how it goes, kind of. Well, let's see what happens. One exponent negative 4. What am I doing here? I can do this in my head. 9.8 times 10 to the minus 3, right? No, minus 5, other way. Right? 4. Right, times 1. Yeah. 9.8 times 10 to the minus 4. Now, down so it's negative. We need to find the electric force. I think we've been writing it E equals F over Q, right? That's how we've been writing it? Yep. If you want to sort of do it this way, and you might have already started this just on your own, F is equal to QE. No, that looks terrible. Don't do it then. Okay? If you want to write it that way, that's fine, because quite often we're trying to find that, right? So it's going to be our charge. 3, F is force, times 10 to the minus 19. I'm going to have to move this over because I can see I'm running out of room. And it's times the E, which is this number, 1.0 times 10 to the 15. Positive, because it's up, right? It's like one is the applied force and one is the friction force. They have to be opposite directions, or they will be. What's the next step? Find the net force. F net, electric force, plus weight force. What would you say about these exponent numbers? Anything about them? Well, they are the same, but should they be the same? Should they be kind of close to each other? Should they be in the same ballpark kind of thing? Absolutely. Okay, we would say they would be on the same order of magnitude is the proper scientific term. That's fancy talk for same ballpark. I get 6.6 times 10 to the minus 4. Oh, minus, right? The only thing that really makes that challenging is the scientific notation. Really. If you can get past that, it's pretty straightforward. I'm going to pause for a second because I want to ask you a couple questions. Okay, so the net force is negative, so which way is this object moving? Down. It's accelerating downward. Is it accelerating downward at greater than or less than minus 9.8 meters per second squared? Is it going slower or faster? Less, right? Because if there was no electric force, there was no Fe up, how fast, what would be the force down? 9.8 times 10 to the minus 4, and it would be accelerating at 9.8 meters per second squared. But because there's a bit of a friction caused by this electric force, it falls slower. Okay? What if the plates, what if the charges on these plates were reversed? Or what are the charges on the plates, right? We've got, it's a positive charge, positive 3.2 times 10 to the minus 19. So this is positive. So what charge is on top? If there's an attractive force up, what charge has to be on top? Negative, right? To attract to it. And we got positive down here. If you reverse the battery, then the object would be attracted down, gravity would be pulling down, and it would be really flying. Kind of thing. Okay. From net force, what do you think the next logical step is? Find the what? Find the acceleration, find the distance traveled, find the speed, all that stuff. I'm guessing that's this one right here. Yeah. So number 2 here, same steps. It says determine the net acceleration, how fast it's traveling after 1.5, how far will it have fallen in this time. Why don't you start that? I'm going to go do my attendance. You get that started. What are the steps the same as this one? Find the weight force, find the electric force, find the net force, find the acceleration. Good. Let's have a look here. Start with the weight force. Mass times gravity, so 4.5 times 10 to the minus 6 times minus 9.8. Kieran, are you with us?
Yeah.
Okay. .5 exponent 6, 9.8. Minus 4.41 times 10 to the minus 5. That's the force down. Find the electric force up. Fe, electric force, Q times E. Charge, 9.2 times 10 to the minus 15. The E value, 3.2 times 10 to the 9. 2.94 times 10 to the 5. And again, those exponents are the same. Say that again? Well, but plus there's also the multiplying as well, right? You can't go by that because there's also, it would be 9 times 3, which would give you 27, right? So there's that one extra decimal.
How do you get -5 then?
Well, I counted on here, right?
Divide it into
What do you mean divide it? I see what you're saying, Graham. You want to take the minus 15 and the 9 and you get 6, right? But but then 9.2 times 3.2 is going to give you 29.4. So you got to go one more to fix that, right? Does that make sense? Yeah? So you got to be careful, that's all. Okay, so now the net force is electric force plus weight force. So, I should have put them, oh no, this will work. 2.94 up times 10 to the minus 5 minus 4.41 times 10 to the minus 5. And again, it's going down because this negative one's bigger.
We got that on my
So I got 1.47 probably times 10 to the minus 5. 1, 2, 3, 4, 5. Okay, that's the same as what the first example was, right? Same steps? Okay, so what's the next step here to find the net acceleration? You're going to need a lot of space for these, aren't you? Right, so now it's going to be F net is equal to MA, 1.47 times 10 to the minus 5. What's the mass? 4.5 times 10 to the 6. Say again? The F net should be negative, right? You are. Down. Thank you.
Man.
My hot hands, I keep pressing buttons here. I hope I didn't have that on pause the entire time. How far does it fall in this time? Do I just go like V 4.95 times 1.5?
Nope.
Why not?
I don't know.
Because that's the final velocity, isn't it? What's the average? .48, and then go, yeah? Go a long ways. How many marks would I give you? Would that whole giant thing be worth, you think?
7 marks.
1, 2, 3, 4, 5, 6,
You missed
7.
Yeah.
I'd say 7.
Oh,
Yeah.